Here we are back in the PLC Professor's lab and workshop. This is where we sort out all of our lab projects with actual hardware. I cannot think of one single lab project that we've done without the actual hardware. Even with CCW and the Micro 800, as you can see, I've got lots of Micro 800s. You see two sitting here. That's a 20 to 50, and then there's an LC70 up here on the shelf, and then here's an 810 over here that I don't use much. And for RSLogix 500, I have my RSLogix Galaxy here, all 5 of the RSLogix with some Ethernet adapters for those platforms that don't support Ethernet. And then of course ControlLogix, I actually have 3 different platforms for Compact Logix. 2 you see here, L45, which is the 4345 platform, which is unique. And then this is the newer Compact Logix. And then I have older Compact Logix in cartons sitting on the shelf, all set up in this kind of a format with a digital field device simulator. I use those on occasion when I'm developing labs, but mostly I use them in class when I do my live classroom presentations. Well, today we're going to do sequential function charts. We're going to start with the very first lab that you did was sequential function charts. Not the most popular language in the United States. There are some good applications for it in certain types of batching and process control, but typically ladder logic probably easily dominates the technical scape in manufacturing. I would say it's probably 90% or 95% of all programming. Now let me clarify what I mean by that when I say 95%. If you take the entire installed base of all PLCs of any type, the sheer number of PLCs and what languages are used in those, then it's 95%. If you only want to count one of a commodity system, in other words, let's say a company makes 250 machines, all very similar, and they all have the exact same program in them. Now you either count that as 250 or you count it as one, since it's really one program in a sense, but it's in 250 different machines. So it depends on how you want to do your accumulation for your percentages. But 95% of all code out there is ladder logic diagrams, no matter what anybody tells you. Probably the worst people for knowing what's out there installed in a plant are the engineers. The maintenance folks know because they have to work with it every day. They're the ones that discover dusty old PLC2s and PLC5s in some back motor control center room. This is, oh, I didn't even know there was a PLC back there. Yeah, open up the panel, there's a PLC2 in there. And it's running, and it runs that line way back there. I mean, there are people in manufacturing plants that don't even know what PLCs are out there. So I spent a lot of time on the shop floor working on these systems. And so this is my estimation that it's 95% ladder logic diagrams. Next would be probably structured text, simply because most of us use structured text for math. Function block diagrams, that's more process control. And process control, I might have to fudge that 95% on ladder logic diagrams. Anyway, so you've got ladder logic diagrams that we covered, function block diagrams and structured text. Now we're doing sequential function charts. So let's get into the first lab. Ladder logic diagrams. This is the, if you want to call it, language that everyone this far in their education is probably very familiar with. You may not like ladder logic diagrams. You may prefer structured text or function block diagrams. A lot of that preference is based on experience or the type of processes or sequences that you need to control. All of the languages have an appropriate place in the controls industry, but these different languages do not suit every process. Some processes are more friendly to ladder logic diagrams than they are to function block diagrams and structured text. And then, of course, function block diagrams is a more graphical representation, and the actual logical functions are implicit in the names of the blocks. And of course, structured text. This is probably the most popular with computer science majors, simply because they are accustomed to working with text-based languages and not diagrams. You would never refer to a text structure as a diagram, whereas with ladder logic diagrams and function block diagrams, they are diagrams, and they're much more graphical, they're more iconic based, they're more visual. With structured text, you have to read it. And then, of course, sequential function charts. Now, sequential function charts are not really a language, even though if you were to ask anyone in the field, what are the languages available in the Logix engine, RSLogix 5000? They would probably say ladder logic diagrams, function block diagrams, structured text, and sequential function charts. Sequential function charts is only a language in the sense that it supersedes the program control available through these other three real languages. A sequential function chart is a chart. If you think of charts, you think of organizational diagrams. For instance, if you were to ask for a chart of your company's management structure, that would be a flow chart of your management structure. And of course, the president or CEO would be at the top, and then you would have lines connecting, and the chart would flow down. That is a sequential chart of the, we'll call it the sequence of command, the command structure of your company. It is a sequential chart. And as we mentioned earlier, a sequential function chart is not an actual programming language, other than it does supersede the program control instruction set that is available in your programming software. We use them because they are easier to read. Simply, when I say read, I mean they are easier to follow in that they are a graphical representation of your process. If you cannot sit down and make a flow chart of your process, then you don't want to use sequential function charts for your program. If you can't easily chart out your process into individual activities that are not necessarily interdependent on the others, then SFCs is not a good tool for your particular project. Another advantage of, or I should say, another reason that sequential function charts are easier to read, easier to understand your process, is that you can add notes to clarify. Now remember that the SFC is visible from the controller. When you hook up your laptop 2 years later, when the project is cold, you can hook up your laptop and the graphical representation, the flow chart with notes, is still there for you to look at. With ladder logic diagrams, many of us do sit down and kind of do a graphical representation of the process, and then we sketch in what we want in each section, and then we sit down and we actually program and put flesh onto it. And the printout of the SFC, the sequential function chart, is a very useful part of your documentation. And then another added advantage is that you can program as you specify. So you could sit down and create a sequential function chart in RSLogix 5000, and as you go through it and you actually create the sequential chart, you can actually do programming write in the individual steps and actions as you go, and that kind of helps clarify the process. Some additional advantages of using a sequential function chart. Now, I would like to reiterate that if you have to struggle to create a sequential function chart for your process, then your process probably does not need a sequential function chart. Some processes are too simplistic. However, some processes really come to life with a sequential function chart. A sequential function chart allows you a graphical division of your process into its major sections. Those are called steps. A step could be a process in a tank. So in that process, you add ingredients and then you go through various actions. So an action, and by the way, minor sections of steps are actions. So an action could be add ingredient A, add ingredient B, add ingredient C. Another action, or it could even be a completely separate step, would be to slice the ingredients. If you've never seen a slicer, it's like an impeller or a blending end of shaft tool that's actually a very sharp circular blade, and it has a mechanical influence on those ingredients, meaning that it actually changes their physical consistency. Slicing could be an action or a separate step if there's a ramp up and ramp down. So you can see that you have major sections, steps, and minor sections, actions, and each of these are graphical representations. Also, repetitive execution of the sections is faster because you're not executing all the code. Typically, in a ladder logic diagram, you put the most likely to be false instruction at the head or the front end of the rung. That way, when the rung state goes false, all the rest of the instructions are executed, but they execute faster in a false state. With program control, using jump to subroutine and all the other program control instructions that you have, code that you don't execute, that you don't jump to, just doesn't get executed. There's no false or true execution, because the set of tools in sequential function charts supersedes that of program control, in that it's much more elegant and gives you much more latitude. Your code is going to execute even faster. Also, because you have a sequential function chart to look at, if you want to look at the whole process, you have much more clarity when your program is displayed on the screen. You go to the sequential function chart and you see immediately what step is activated, or steps, or what actions they're highlighted. Program and debug time is reduced because you're working with a 1,000 rung program, a ladder logic diagram of 1,000 rungs. You burn up quite a bit of time navigating to the different sections. With a sequential function chart, it's much simpler. Also, debug time is reduced because you typically debug one step at a time. Once the steps and the actions within the step are debugged, then the organization of the steps is a very simple editing process. And of course, troubleshooting is much easier and quicker for the same reasons. Also, if the process gets hung up because something cannot complete of a machine fault, the machine faults are pinpointed much more accurately, meaning that it's easier to go right to the machine fault. You don't have to drift around through a bunch of code looking for it. And then, of course, simpler editing and process improvement. As we said, a very elegant means of program control. Speaking of program control, because at this point, if you're watching this video and you're watching it because you completed the projects in the RS5000 manual, then you have already gone through all the ladder logic diagram projects and you've used the program control somewhat. Now, the program control in RSLogix 500 was limited to these half a dozen or so instructions. Looks like there's 8 instructions altogether. Jump, label, jump to subroutine, return, subroutine, temporary end, master control relay, and suspend. Now, not everybody calls the MCR master control relay, but in the era of time when all of this was created and then transformed into a programming language, a master control relay controlled the power to a section of the relay control panel. In particular, something everybody would understand, the master control relay was controlled by a set of conditions, one of which was an e-stop button being closed, normally closed, light curtains, contacts being normally closed. So as long as the e-stop was not pressed, light curtain was not interrupted, then the master control relay was energized, and it supplied power to a section of the relay control that controlled actual motion and other points of the process. And if you hit the e-stop or broke the light curtain, then you de-energize the MCR. These are the program control instructions that you have with RSLogix 500. Now, RSLogix 5000 has a much richer set of program control instructions. And we're not going to go through all those, but you can see everything that is up above is pretty much found down below. I don't see suspend, but there's other functions. You also notice the always false instruction, AFI. That's a program control because typically people put that at the head of the rung if they want to temporarily not execute that rung. Or rather, I should say, they want the rung to always execute false, so it has no influence on the program. And then of course, there's a no operation. And that is typically used when an HMI is not available. People will create rungs of logic that are true if on instructions, XICs, with specific tags being addressed by those. And then at the end of the rung, you have a no-op. You don't have an actual output type instruction. You have a no-op. These rungs are normally put strategically through the program, so when you're troubleshooting certain sections of the code, you have one of these, call it a view-only type rung, where you can see the state of the individual bits that are influencing the code that you're actually looking at and trying to troubleshoot. Now, I'm not going to go through the rest of these program control instructions. You could do the same type of program control with these instructions that you do with sequential function charts. But once you went through the process of writing the code to do that, with timers and one-shots and everything else in your main routine where you normally have your program control, you'll go back and use sequential function charts. They're much simpler. And remember, a sequential function chart does not have to be complicated. It could be a very simple chart with no more than half a dozen steps in it that provide control to JSR to your subroutines, and all the subroutines are ladder logic. Now that we've laid the groundwork for sequential function charts, most of this information you knew before you actually did the lab projects. Now that we've laid the groundwork and we've got everybody on the same page, now let's actually go through the lab projects from the manual. This lab, Sequential Function Charts, was a section in the languages lab as a whole in the RS5000 manual. So we already had a project that we had created. You can't see the title bar because I have it outside of the screen capture. But my title says Function Block Diagrams in, and then there's a name in there that I've created in the process of going over and over again, going over these labs many times. We'll deviate a little bit. Also, if you've been watching the lab discussion lectures, I tend to go quite a bit further in the lab discussion than I went in the actual lab. So it's not just a lab discussion, it's also a lecture. Not just a wrap-up, but it is additional information. The first thing you always want to do when you start a lab is to check and make sure that you have communications with your controller or communication with your controller. So you would open up RSLogix and you would make sure that RSLogix could see the controller. There's our CompactLogix processor. So always check in RSLogix before you get too far down the road to make sure that you have communication with the controller. Don't wait until you try to download and then you have to sit through a timeout because Lynx cannot find the processor. You probably also remember from the previous lab projects that we used some program control simply to allow us to use the same tags for many different routines without interference. If you look at my list of routines, you'll see that I have added 3 more, Sequential Function Charts 1, 2, and 3. Now there's nothing in these routines yet, but I created these so they're there waiting when I go through these lab projects. Now you may not remember that we had more than one routine for function block diagrams and ladder logic diagrams. The contents of these is irrelevant to this particular lab. I just didn't want you looking at these routines and wondering what they were doing there. These are left over. The FBDs and the LLDs and the structured text are left over from the previous labs. In the main routine, we had a method of controlling which routine was being executed, and we had this second branch to allow you to toggle the different routines on and off. So we're offline right now, we're not in the run mode, but if I toggle this on, right click, toggle bit, which I'm not going to, then I would turn on this bit in memory and we would be executing ladder logic diagrams 0, 1. However, we would also one-shot to unlatch all the other bits so we knew none of the other routines were executing. So I probably have added this code for the sequential function charts as well. So you can see if I toggle that bit on, then it will one-shot these unlatches that will unlatch these other 2 bits that would allow these 2 routines plus all the other ones up above to run. You don't have to do this code. You could simplify it down to, we'll just take and copy this one, Control-C, Control-V, and then we'll delete that. It could be that simple. And that just means that you have to go in and toggle this bit on when you want to execute this subroutine, but you have to toggle it back off if you want to execute a different one. This code just allows you to kind of one-stop shopping. Toggle this one on, it runs that routine. If you toggle a different one on, it makes sure all the rest of them are off and just the one that you want to run is running. There are many other ways to do this. Actually, much simpler means. However, this gives you the idea. The other means aren't very explicit. The control is implied and not actually explicit. Here you can see exactly what's going on. So let's close this routine. We don't need this routine. Now we'll leave it open. That way we have the tab down there and we can easily go back to turn on whichever routine we want. I'm going to delete that wrong because that was an extra thrown in. Right now nothing is activated. You can see that this bit, one-shot double integer bit 7, is on right now. That's kind of a hangover from a previous project. So I'm going to right click, toggle that bit off. It really wouldn't hurt anything, but it just looks a little odd. So let's open up Sequential Function Charts 1. Double click. And of course, if you were to open up an empty ladder logic diagram, you would get a empty rung. When you open up a sequential function chart routine with nothing in it, it assumes you want something in there, so in it pops. I'm going to hit delete because they're both highlighted, and we'll add our own at the rate that we want to add them. In the lab project manual, I had you go up here and you can either click and it drops one down, or you could have drug it down. Your choice. These little mouse overs are nice if you want to get a little more information on what these different tools are. We'll just breeze through these real quick. This one's going to give you a step and a transition. This one's going to give you just a step by itself or just a transition by itself. These are actions. This one is an action with a body, and this one is simply a Boolean action. This one is a selection branch diverge, meaning that you want to diverge out from a transition or from somewhere in your code, and you want to go to a path of which you can select from that path using expressions. This is a simultaneous branch diverge. The difference between these two is this, you have a transition if you want to follow that particular path. This, all of the paths are going to be followed. You're going directly to steps. This will converge either this or this back together. So if you open up a selection branch or you open up a simultaneous branch, you bring it back together with a converge. When you select a selection branch diverge or a simultaneous branch diverge, you get two elements or two branches, if you will. This allows you to extend the branch. This is a stop if you want the program to stop, and the rest of these we don't care that much about other than maybe text box. I had you drop down a step and a transition. I had you name it first. So to name it, well, you click on the Properties button. You go to the tag and you name it. We had you name it Start. I also told you to just leave this as is. We won't go over all of these details in this particular lecture. We're going to save this for a more advanced lab on sequential function charts, probably in volume 3 of the manual. Sequential function charts aren't that popular, so there's kind of a diminishing return on any effort put in other than just getting you started to give you some basic use of sequential function charts. So we're going to apply, OK, and now we have our step named. Now we want to add another step. So I had you click on this and bring it down. You can drop it and then do a connecting line, or you see when it turns green, let go, and now you have that step connected directly to the bottom of that transition. Since this step is in focus, we can simply go up here, that is if we want another transition, and that's what I had you do in the lab. I said because this is in focus, that's in focus, that's in focus, that's in focus. Whatever's in focus here, if I go up and click on something, it assumes you want it right after whatever you had in focus. So this step is in focus. We click on transition, it drops one right in, already connected. A bit of a time saver. This is something like adding instructions in ladder logic diagram. If you click on an instruction in the toolbar, it is appended immediately after the instruction that had the focus on it. In Windows, focus is something referring to the element on the screen that Windows thinks you're interested in. And of course, you do that by clicking on things to switch the focus. If it does not land where you want it when you click on it, then drag it and drop it as shown. As long as we have the focus on that transition, let's add another step. So we just click, it drops right into place. Now you notice that these are auto naming as they're added. We edited the name of this step to be Start. However, this was auto-created, transition 0 and transition 1, step 0 and step 1. We don't want to keep those names, but for right now, we're going to throw in the structure, and then we'll come back and change the names. So we have in 3 steps and 3 transitions. Well, actually, we need one more transition. Since this is already highlighted, we will just, in focus, we'll just click on transition, and now we have our 3rd transition. Let's select the properties for first transition. So we click on Properties, we go to Tag, and we have a Boolean tag created. However, I want you to change the name to Run Product 01. You can put underscores or not. Typically, if it looks good without the underscores, it looks clear. Now, without the underscore between the T and the 0, it's not as readable. So if it's very readable without underscores between some of the words, save the space. Leave out the underscores. Technically, I suppose that is readable, that the 0 gives you a delimiter between product and 1. However, I don't quite the looks of that. I like the looks of it. So I'll put the underscore back in. Now you see I've renamed this tag. However, this transition is still not happy. You see the question mark? Remember, this is a transition. And this transition leaves this step and activates this step. But there has to be a condition. So we'll double click on the condition. And we have a field here. Now, and I don't know if it's screen resolution or if it's just a deficiency in this editor. But typically you have to stretch this out a little bit. So you can make it as big as you want. You can make it quite small. But usually if you're going to browse for tags, a little narrow box isn't going to do, because when you right click and say browse tags, you don't see the drop down arrow. And we want to type something in to get us into the right area of our tag database and then select a tag. Double clicked, we expanded the little pop-up, we right clicked, and we went to browse tags. But really I would normally type in LO for local, and that gets me right to those tags. In this case we're looking for local 2 input data bit 0. So local 2, expand. These little mouse overs can be kind of annoying. They tend to get in the way. So you have to kind of get used to know where to put the cursor or the pointer so it doesn't annoy you. We drop down the list and we pick 0. Now you see 0, 1, and 2 are already picked. So it says used, not used. Okay? It's used in an integer, but it's not used as a bit. Okay, so it says use no. And this is an integer because remember that these are 1769 I/O cards. They're not 32-bit dense like the 1756 modules are. So let's pick 0, and then we can just click anywhere and voila. There it is. Our transition is happy. You see, this transition is not happy. Happy transition, unhappy transition. So we have a Boolean expression in here. Now you're saying, well, it doesn't look like much of an expression. In text-based languages, if you have a tag and that's it, it is implicit that if that tag is true or it's in a 1 state or a high state, then the expression is true. So this says transition and run product 1 if local 2i data 0 is on. In other words, that input is on. So this is kind of like a true if on instruction, and it's addressing that bit in memory. Now we're not going to go through this process of browsing for tags all the way through this lab project. We're going to do enough of it and enough of editing with sequential function charts, especially procedures you haven't seen before. But eventually we'll thin it out. It's assumed that you've already caught on. You could have pressed enter or just click. The focus is still there. So now we want to name steps 0 and step 2. We go to the properties for this step, go to the tag. We want to name it A step 1. A underscore step 01. If you didn't name your steps exactly the same way I did, don't worry about it. It's arbitrary. You're creating a tag structure where the information data, the data type of step, stores the status and any other pertinent data about this step. Now we want to name this step tag, and this step is named A step 2. Very clever names. A step 1, A step 2. Then I had you finish editing the tags and IO assignments to match below. This needs the name change to run step 2, tag. And again, if I named mine a little bit different than what I had you do in the lab, not to worry. And I might have had you do it in a different order. I think this is run step 2. And we will name it finish product 1. And then of course we need the tags. Double click, stretch this puppy out, right click, browse tags, LO for local, and we want bit 1 this time, so local to iData bit 1. There's another way you can do this. We'll take and we will select that, Control C, come down here, double click, and then paste it in there. Control V, backspace 2, enter. Now that we have everybody happy, and I'm going to reduce the size so you can see the whole thing. The last thing that we have to do is connect the end back to the beginning. And it should pull the line all the way around the side. I have had it just lay the line right across the top, and that's illegible. If that happens to you, delete the line. You delete it by right-clicking on it, delete wire. So I'll put it back in there. When it turns green, let go, and it pops around the side. So here we have a complete sequence, a complete sequential function chart, and we're looping back, so it just continuously runs. Now this is your preference. With ladder logic diagram, especially in the continuous task, all the code executes in sequence continually. Now if you have program control in there, of course it doesn't execute that code where you don't jump to subroutines. Now we want to save, download, and go online into the run mode to test your logic. So we go up to communications, Who active, you could hit download and you'd probably be okay. Who active, I like to look to see where I'm going. I can also set the project path. If I have a processor picked and I set the project path, then this other button that was just a direct download knows to go to that controller. Now we only have one controller, so it's impossible for us to download it to the wrong controller. But in the real world out there, if you're on an Ethernet network and there's 2 or more controllers out there, the possibilities of accidental download to the wrong destination is possible. So we click download, and then I'm going to pause the recording until the download is finished. It's been a while since you've downloaded. This message always pops up. This is a default message. It's good to read through it once. It's necessary to read this every single time you see that. Basically, it's just a bunch of warnings. So we hit download. Here we actually are starting the download. This is good because this does happen. It happens to me often. Notice complete 4 errors. So let's go find what these errors are. Some of these are warnings. You see it says warning. And the reason we have so many warnings is because, remember, we're using some of the same information in multiple routines. So you see most of these are referring to routines we're not even working with. However, let's scroll up. You see if you click on one, it takes you right to the error. See, it's opening these up. We don't want these open, so I'm going to close all these routines back down to get it down to just these 2 main and sequential function charts. And I'm going to continue up until I see an error. There's the 4 errors right there. Okay, this is good. Initial step required. I did forget to do that. I don't even know if I told you in the lab to do that. Maybe I did it and never mentioned it in the lab. So we have to fix that. Logic cannot be reached. Okay, I believe these 3 errors are caused by that 1 error. If we go up to the start, we want this to be the initial step. When you have a loop like this, It's kind of like in function block diagram when we created that loop to simulate a certain condition, the latch condition that you would have using the OTL and OTU. In function block diagrams, you don't have that specific instruction. So we had to create a loop and then we had to reconcile the loop. This is really the same thing. So we can pick any step to be initial. We want start to be the initial step. So you simply right click on the block or the step that you want to be the initial step and you click on initial step. Now if we verify, see 0 errors. So there was really only one error. However, because it couldn't resolve the first error, as it looked down through, well, none of this is even reachable. Remember, it said code not reachable. This was good that this popped up. I didn't plan this. Every once in a while I luck out and get a freebie. Now let's download this again. This time I'm just going to say download to save some time. Again, I'm going to pause and then come back when it's done. The downloading is finished, and as you can see, we are in the remote program mode. This is what you see when the download is complete. 0 errors, and there are 3 warnings. If I drift back up, they are actually 3 sections. This one is specifically duplicate destructive bit. That means that bit 2 of that word is used in many different places. Notice that none of these refer to Sequential Function Chart 01, the routine that we're actually working with. So you won't see all of these warnings in your code. And you see this is for bit 0. So we'll close that. That gives us the full screen to use. Our Sequential Function Chart is a little large. We could remove some of these toolbars to give us more vertical space. I will just reduce it down, and hopefully you can see this on your screen. Actually, I think I will pull out this toolbar and this toolbar. You see that gives a little more vertical space, and then this. The reason this is so slow responding is because I'm using RS-232.38.4, not Ethernet, because I have Ethernet tied up doing something else. That's a little bit better. We'll go one more. Okay, you see that was very awkward. I did not like that process at all. So I've pulled these toolbars out from up here to give us more vertical space so we can see our sequential function chart a little easier. We're still in the remote program mode, and that's fine. You see there's nothing highlighted here, so nothing's running. I'm going to put this in the run mode, which is what you did in your lab. Change to the run mode, and you're going to see one of the steps should be highlighted green. One of them should be highlighted green, but guess what? We're in the remote run mode, but what did not we do? I should say, what didn't I do? Well, what routine are we running? Let's go look. We go to main, and if we scroll, you'll see none of them are activated. And we want Sequential Function Chart 01. So we go down here, we right click, toggle bit. Now we'll go back to Sequential Function Chart 01. You see the start is highlighted. That's what we were expecting to see. So we're in the start step. This is transition to go from this step to this step. So we've got bit 0, bit 1, and bit 2. These are switches on our little hardware demo unit here. So I'm going to press the push button that is associated with bit 0 of that data word. So I toggled it, meaning that I push it on and then released. It's not necessary to maintain it. So that transition went true, and it stepped to a step 1. So we have start, a step 1, and a step 2. And of course there's no actions in step 1, so we go ahead and run step 2 by pushing the push button associated with bit 1. And that transitions to 2. Then the transition from a step 2 is the push button associated with bit 2 of that data word. I push that, and we're back to start. See, sequencing through them. it sets right there on start. It doesn't look at step 1 and step 2. It's not like RSLogix. So this would be analogous to running the main routine in a RSLogix diagram program. And then you have permissives, conditions, on the rungs to jump to a subroutine. And once it runs that subroutine, it comes back to the main routine. But unless you have a condition true to jump to the next subroutine, which would be step 2, then it just cycles back to start, and then it continually runs step 1 as long as that is true. So you see, you can write code to perform this exact same function. That might have even been a good thing to do in the lab, but these manuals, I try to keep them well under 200 pages to make them manageable, not just for the printing price, but for handling. So I try not to waste paper. Now it's time to add some actions. I didn't like the menu layout, so I put it back close to what it was, and I used the geezer buttons, make it bigger, make it smaller, to bring this more into view, to make it a little bit easier, because I realize that you may be watching this on a mobile device and you have at best a 5 or 7 inch screen. So I'm trying to be conscious of that fact and make things a little bit bigger. We want to add some actions. To do that, we have to put this into the edit mode. So we go up to the little pencil piece of paper, click on that. That puts this in the edit mode. Now you see the pencil piece of paper. That way you know it's in the edit mode. You right click on the step and then you select add action. Add action. And we want to leave it as a non-stored. If I drop this list down, we would see all the different action qualifiers. We're going to go to the properties button, and we can drop the list down here. So these are all the different qualifiers. We're going to leave it non-stored. In a later portion of the lab, we will explore some of these other qualifiers. We're going to go and leave all this alone. Now, the action order, we only have one action, so there is no order. But if we had more than one action, they would all be listed here, and we could rearrange them. We could move them up and down. Let's go to tag, and we're going to name this energize_M01. Basically, energize motor 1. Okay, that's the name of the action. Now, that doesn't actually do anything. That's just the name of the action. Remember, we're online in the remote run mode. We're doing this online. We're not in the program mode. These edits will cause Sequential Function Chart 01 to reset to its initial step along with its stored actions being reset. Well, we're in the initial step already, so that's not going to change anything. But let's say that we were in step 1 and we were editing step 1 actions. This is warning us that when we complete these edits, it's going to jump back to the initial step. After you named it, then I had you double click in the action field, and again you want to stretch out this little pop-up so you can see the drop down list if you browse for tags. And I have you browse for a tag, so right click, browse tags. Then I had you select the drop down. We'll do that. We'll select the drop down. The problem is you see all of these other tags from the previous labs that have nothing to do with this lab. But I'll do it that way once. We'll scroll down till we hit local, because we want I/O, and we're looking for local slot 1 output data bit 0. So we'll go to local slot 1 output data bit 0. You see they're already used in other routines. We'll pick that one. Then you can hit enter if you like. Actually, enter doesn't get rid of this box. That's why I tend to just click anywhere outside the screen, and now we have our tag in there. However, that's not all we want to do. That just gave us the tag. Now we want to actually do something with that tag. After the tag, remember this is an output. So I'm going to have space, colon, equals 1, semicolon, and then enter. Now I have an actual expression. We want this tag to equal 1. All inputs off, finalize all edits, and put the controller back into the run mode. Well, we never went out of the run mode. So you could have gone to the program mode and this edit would have been just a little less cumbersome, not much. So we'll finalize all edits. We get our usual warning and we'll close this. We don't need that. And we don't need that. Now I'm going to de-geyser this, or geyser it, whichever way you want to look at it, so we can see what boxes, what steps are green. We're in the start. So to get out of the start to the next step, we have to transition. So we push the push button associated with bit 0. That activates step 1, and there's only one action in there, and that is to turn on bit 0 of that output data word. And I look over at my little demo, and I see the LED is lit. Now if I continue to step through, now you see the step now, or a different step that's active. I want you to also notice that not only did a step 1 go back to being not activated, but the action, energize motor 01, M01, it is also not active now. We went into that step, and if you have a hardware demo that you're using, if you look over, we left that step, but guess what? That output's still on, isn't it? All we did was turn it on. We never told it to turn off. This isn't like an OTE. OTE instruction has a true execution and a false execution. An OTL has a true execution, no false execution. An OTU has a true execution, no false execution. An OTE has a true and a false execution. So when you execute an OTE true, it turns something on. When you execute an OTE false, it turns something off. In this case, all we did was turn it on, and then we went on to step 2. And in the lab manual, it says probably something unexpected happened. If it did, what was it? Well, when you went from step 1 to step 2, the light stayed on. Step through the sequential function chart until you see the behavior that is not the same as you would expect from a ladder logic diagram. Now, I already went through and explained why. Of course, when you did the lab, you didn't have the benefit of me talking while you're doing it. You would have stepped through. And so we go back to start. And then we go to step 1. Of course, nothing changes. Because when you went back to step 1, well, that output's already on. So turning it on again does not change anything in your process. Input 0 transition the routine, a step 1. And the only action was to turn on output 0. Nothing in this step is true, and therefore nothing has a true or false execution within the step. It's just a Boolean expression. Turn on that output. So does output 0 ever de-energize anywhere within this routine? Does it de-energize anywhere in the whole sequential function chart? Now ignore the fact that there are other routines using the same I/O tags, albeit they are not executed per the JSR instructions in the main routine. Although these bits are used in other routines, we're not executing those other routines. This is an extremely important characteristic of sequential function chart, transition, and step. Also make note that the action stayed active until you transition into the next step. That's because it's a non-stored action. So now we'll change the qualifiers to something else and see how the behavior changes. Let's take a break. We'll make this the end of part 1. This lab wrap-up lecture recorded at about 3 hours. I will try to clip out quite a bit of it, but I don't want to put a video in the system that's of that length. So let's stop it right here. Stretch your legs, get something to drink. If you're falling asleep, go run cold water over your face. We'll see you in part 2.